understand how videos quality can be measured, and then use that to improve the resource allocation in the wireless networks or mobile networks in particular, right? In terms of the overview, this is the overview for the presentation. We'll start with basic video demand over network. What kind of video demand is present currently over the network? Then we'll spend some time over the dash architecture. What is dash? How is it used, right? And then we'll discuss a bit about QoE. What is quality of experience? How should we be measuring quality of experience? And then various type of issues when transmitting video over a network, like rebuffering instances. We have created a video database as part of the study. So I'll elaborate that a bit. And then how to perform machine learning based modeling for this quality of experience. And finally, how to use this QoE, which is generated through an ML based model, and perform optimal resource allocation for wireless video transfer. Right, that's by and large the outline for the presentation. So in terms of the demand for video, as you all might be aware, the demand for video has been rapidly increasing. It has been growing at 63% from 2016 onwards, and by 2021 it is expected to be 70% of the IP traffic, videos only, right? That's a huge percentage of traffic. Within 4G networks, it was 70% already in 2016, and it is expected to be 80% by 2021. Please note, whatever discussion we are having now, this also qualifies as a video traffic, because essentially in Google Meet software, a video is being recorded and the video is being transmitted from my end to all the participants. Actually, it's a bidirectional video transfer, right? So this also adds to this increasing video usage. Further, in terms of the global IP traffic, it will be 82% of the global IP traffic, videos itself. So huge amount of videos are being transmitted across the network, both wireless, mobile, 4G, as well as overall in the internet perspective also, right? So then there is a huge demand for videos, and it's an interesting topic to study as how this demand can be catered. When it comes to various resolution types, these are the current standards that we have. So for example, we have SD video, which is 2 Mbps, or which requires 2 Mbps. There is the high definition HD video, which requires 5 to, maybe I just zoom it a bit. Yeah, 5 to 7.2 Mbps. And you have ultra HD videos, which are 15 to 18 Mbps is the requirement, right? In terms of the connected 4K TV sets, this itself is increasing 27%. As you see, from 2018 to 2023, they are expected to almost more than 3 times, right? So overall, not only the video demand is increasing, the quality of video or the amount of data requirement for each video is also increasing. As we are heading from SD to HD to now UHD, as you see here, it has increased exponentially. So even if the number of videos transmitted would have remained the same, the demand by the same video because of increased resolution would increase exponentially. But in our case, both are increasing. So it's like a double hit on the network. Now, some recent data. Because of COVID, there is significant increase. Well, unfortunately, we should say, but there is a significant increase in the video consumption. So this is data from Facebook, Netflix, YouTube, Facebook app, as well as the website. And as you see here, in terms of the app, there is some reasonable increase in data, maybe 1%, maybe 0.3%. But in terms of the website, the demand of the video consumption has increased substantially. So there is a 27% jump in Facebook, 16% jump in Netflix. And when we say 16% jump, this is over a matter of few weeks. So within few weeks, substantial increase has happened in the way video is consumed across the globe, right? So given this significant increase in video demand, how is it catered to? How do we transmit video over the internet? So one of the most common platforms that we use across the globe for watching videos is YouTube. And YouTube utilizes Dash as a framework. What is Dash? Dash is essentially dynamic adaptive streaming over HTTP. So if you have an internet-based network which is using HTTP as a protocol, for example, in your browser, then this allows you to transmit dynamically and adapt the streaming of the video over the network. What it requires is it requires an HTTP server, and it requires a Dash client. So this is essentially an algorithm running at the client side, where what the client is doing is it is requesting for the MPDs. In this case, the MPDs are the media presentation descriptions, where each MPD consists of multiple segments, and you have them at a particular resolution, and you have it available for multiple resolutions. So the same file, for example, is available in SD, is available in HD, and is available in FHD. It's just for illustration. You can actually have multiple resolutions and things like that. Now, based on a control heuristic running at the client side, the client, when it is receiving the MPD, it passes it to the media player, each segment by segment, and the media player renders it. Based on different control heuristic, the HTTP client then requests the next set of segments, right, and then renders it. So what can be done is, if the video quality is improving, you can move on to higher resolution segments. If the video quality is deteriorating, let's say there is a rebuffering event happening, you can potentially request lower resolution segments also. So that's the advantage of using Dash as a framework or dynamic adaptive streaming as a framework. So now, in terms of the wireless video streaming, please note when we are using our mobile phone which is connected to the base station, that's a wireless channel. Or when you're using, let's say, Wi-Fi and connecting to an access point in your house, that is also a wireless, channel. So wireless video streaming has a couple of additional challenges. One is the channel conditions themselves are time varying. For example, if you're watching a video in your mobile phone and you're moving around, the channel between your mobile phone and the base station is changing. So this affects the resultant data rates, and which in turn affects the rendering of the video, or can potentially affect the rendering of the video. Please also note, even if when you are not moving, let's say you with your mobile device are stationary, the base station is also stationary, but the nearby environment can change. For example, let's say there were certain vehicles parked earlier, because of which you were getting some reflected signal, and then all of a sudden those vehicles move. So the time varying nature of the channel is not only because of the transmitter and the receiver, it is also because the environment itself can change. Second thing is the resources are limited and they have to be shared. So for example, in terms of bandwidth for LTE, you might be using some 10 or 20 megahertz bandwidth, which effectively can translate to, let's say, 40 Mbps. But that 40 Mbps is available for all the users connected to that particular base station. If you have 100 users connected, then effective rate will be just 40 by 100 or 0.4 Mbps on an average. So then for this wireless medium, because the spectrum is so costly, the resource is pretty limited. You can always say for Wi-Fi that is not the case because it is unlicensed spectrum, but then Wi-Fi has its own issues in terms of the availability of channels and the quality of experience and the quality of service. So for this one, we'll focus on mobile networks in particular, because at least they have the advantage of coverage and ensuring certain quality of service or quality of experience. So in such a scenario, you can have client-driven streaming based on QoS heuristics such as throughput and buffer level, where you can have, as I have shown you in the previous slide, you can have a Dash client, where the Dash client knows what is the current throughput level, what is the current buffer level, and based on that, it can decide, okay, please send this kind of a segment next. But this kind of a setup is actually agnostic to the video transmission, and it can be suboptimal because it may not be aware of the actual quality of experience of the user, right? So which is where our proposed work helps, because quality of experience is not always equal to quality of service. For example, quality of experience is actually subjective. It depends on the overall acceptability of an application or a service by the user, right? It depends on objective measures like resolution and encoded bit rate. So for example, if the resolution is higher, but of course quality of experience will be higher. Encoded bit rate, if it is better, then quality of experience will be better. But at the same time, it is also a function of cognitive factors like variability in perceived quality, memory. So for example, if there is a rebuffering event, how long was the rebuffering event, it will affect my quality of experience even when the video starts, even if the video is in very high resolution. So those kind of subjective things have to be taken into account while measuring this quality of experience, right? Sorry. So most existing QE models, they do not evaluate the perceptual QE. Most of them consider the objective measures like resolution, bitrate, those kind of things. Whereas overall quality of experience, which can be collected. So you can collect quality of experience like you can say you can have an opinion score at the end. So if you go to Netflix and all, just a second, give me a minute, please. Yes, sorry. So I was saying you can actually collect mean opinion scores. So for example, if a lot of you might be using Amazon Prime and you might be using Netflix, then for such platforms you can get these IMDb ratings, which is essentially saying for a full video of that particular movie, you can rate it. You can get a mean opinion score on top. But that's a rating of the video which cannot be used to decide runtime, that what will be the rendered quality of experience. See, it might be a very good picture, but if every 1 minute there is a rebuffering instance where the picture stops, then your quality experience as a user for the same video can be relatively much poorer. So the overall mean opinion score cannot be used for streaming or continuous quality of experience analysis, right? And the perceptual QoE in streaming, it involves non-linearity. So it is not that if I double the resolution, my quality of experience doubles. No, beyond a certain point, a user may become agnostic, especially given the screen sizes. The user may not linearly increase, the quality of experience of the user may not linearly increase with the improving or increasing objective measures. Also, the perceptual QoE has memory known as hysteresis effect. If for past 2 minutes I am watching the content at excellent resolution, then for a while, even if the resolution drops, typically I am okay. This kind of a behavior is observed in practice. So this is happening because of the human brain. We have this notion of hysteresis effect. Now this quality of experience, the perceptual QoE, it is typically determined by 3 major factors. The source video quality, which is a pristine video, uncorrupted video, no artifacts, nothing. Second thing is the time varying quality, how it is varying with time. And third thing is the rebuffering. If there is any stalling happening, if there is any outage happening in playback, then that also affects my perceptual QoE. In this study, we model all of them using ML or machine learning. So that's the motivation of first explaining what we are trying to model, and then we'll come to the AI and the ML part of it, right? So moving forward, this is just to illustrate. So I have we have put images here where you have the pristine original image, you have the same image at 400 kbps and the same image at 100 kbps. As you see, with decreasing rate, there are these artifacts being introduced in the rendering, which is not good for your quality of experience. So quality of experience obviously decreases as we go from original to 400 kbps to 100 kbps, right? So now the question is how to measure this quality of experience, which is time varying in nature, right? So in this direction, there are existing works, for example, by Soundararajan and Bovek, or even by Chen and others, where they have shown that you can measure subjectively the time varying quality, also termed as TVSQ, where this subjective time varying quality is not the same as STSQ. What is STSQ? STSQ is essentially it captures the instantaneous video quality using VQA metrics. So this is kind of like the objective measure. The objective measure of your video is not equal to the subjective measure of your video. So that is what has been shown in this study, where this red, for example, is an objective measure, STRRED, right? And TVSQ is the subjective video quality with a 95% confidence interval around it. So this is essentially to highlight that objective measures need not directly translate into subjective video quality. For that matter, here the objective measure is very high, but the subjective video quality is low, right? So this study was done way back, let's say 2013-14, when we were also starting this our own study in this direction, and it was motivated in some sense by these existing studies on STSQ and TVSQ. So then this STSQ, it can be used to predict, because STSQ is an objective measure, right, of the instantaneous video quality using any of the VQA metrics. It can be used to predict TVSQ, right? So you can have quality varying video coming in with some input nonlinearity. You can apply some sort of a filter on top, an IIR filter, and try to model through output nonlinearity the corresponding TVSQ, the time varying subjective quality. So this is a work done by Chen and others, where they have shown that this kind of a modeling can be done. Motivated by this, you can compare. So here we are comparing various VQA metrics over LCC, RMSE, root mean square error, and other measures, and we are trying to just highlight how they compare, right? So in this case, you can see, for example, a lower RMSE is better, so MS sim is better here, right? So they say you can compare over these various metrics. So given this, now what we want to do is, what our contribution was, we added this notion of modeling rebuffering effect. So all the existing subjective video quality ML or machine learning based models, they were not considering rebuffering effects at that point of time. Please note, since then there have been many studies. Our study we have proposed, others have also proposed since then, but at that point of time no such study was there. So we said, fine, we should model the rebuffering instance, because it is an essential aspect of video quality for any user. For example, if you're using a video or you're consuming a video on a smartphone, and all of a sudden there is a rebuffering, this circle starts rotating in a YouTube video rendering, that is really not a very good quality of experience. So we thought we should model that also in the same QAE model. So with that as a model, as the motivation, we thought we'll model the nonlinearity as a sigmoid, and we'll consider a hysteresis using an IIR filter, and then there is a scope for better improving this TVSQ by using rebuffering also. So then we had this setup in our first work, where we had a video source which was coming through a content delivery network. It was communicated using maybe a proxy server, or you can directly send it through a node view also, where the rate adaptation is happening at the proxy server, and a QoE based streaming is being performed with suitable resource allocation. So in this case, we recomputed the STSQ. So please note, STSQ computation was already available. We recomputed it based on rebuffering instances. So what we said was as follows: if there is a rebuffering instance, right, which is delta TB is the rebuffering instance. If rebuffering instance is not present, delta TB is 0. Then STSQ is computed as was computed in the existing literature. On the other hand, if the rebuffering instance is less than a particular threshold, it is equal to e to the power minus lambda delta TB. It's an exponentially decaying function. And beyond a certain threshold, it doesn't matter what is the amount of rebuffering. So for example, if the rebuffering is 2 minutes or 5 minutes, actually people tend to stop watching after, let's say, 1.5 to 2 minutes. They would be like, I don't have coverage. So then whether it is 2 minutes or 10 minutes, it doesn't matter, because the person is anyway not watching the video anymore, right? Or the quality of experience measured through STSQ remains almost the same, right? One more thing is, beyond a certain outage, the quality of experience is also a function of what was the quality of experience in the previous instance when the outage had not happened. So that is why we have made it STSQ-T as a function of STSQ-T minus 1, which was the experience in the previous instance when the video was correctly rendered, e to the power minus lambda L. So it keeps on decaying exponentially beyond the period L, with L as the constant factor here, but it is a function of the previous rendering, right, after a certain amount of time. With this, we defined our enhanced version called ETSQ, which was a function of this novel STSQ prime or tilde in this case, where I take my input features, I pass them into the STSQ. If there is any depreciation due to rebuffering, I recompute STSQ tilde and then use that to predict my TBSQ, which I call as ETBSQ predictions. So with this, we were able to show certain improvement in our first work in this conference article in WCNC, which was way back 4 years ago in 2016. That is when Dr. Nagbhushan started working in this topic towards his PhD thesis. So then we realized there is a requirement for a database itself, because no such database was available at that point of time, which provided subjective video quality variations as well as rebuffering instances. So motivated by that, we created our own database where we had 54 videos. It was a mix of full HD and UHD videos with time varying quality and rebuffering distortions introduced artificially into those videos, and then conducted a study using subjective evaluation of QoE impairments in a continuous manner, right? So these were the resolutions considered. So we considered SD videos at 300 kbps, 600 kbps, HD videos at 1200, 2400 kbps, and full HD and ultra HD videos at 4800 and 9600 kbps, where the corresponding resolutions are as shown in this table, where diverse frames per second were considered. So we considered 24, 25, 30, 60 frames per second, and video length of the kind 120 seconds were considered. So short videos are considered because for a subjective study, if you take a very long video, then a lot of other issues start arising based on how you are evaluating the video through the subject. So purposefully short videos were considered, and they were all encoded using FFmpeg encoding. Further, we considered various rebuffering durations. It's a 120-second video, so we considered a rebuffering frequency of 0.5 per minute or 1 per minute, 2 per minute, up till 5 per minute. And the duration of the rebuffering also was varied from 1, 2, 3, 5 to 9. And this is how we randomly allocated UHD, full HD kind of videos, so that there is no bias in terms of any particular video kind, right? So this is just to elaborate how we vary the rate levels. So if there is a rebuffering duration, the rate level drops in this fashion. The rate level drops from 4 to 3 to 2 to 1 if the rebuffering duration is of this order. Similarly, it increases if there is no rebuffering, then it increases in this timestamp. That from 0 to 3 seconds, if there is rebuffering, then it comes to 1 rate level, and then after 3 seconds it jumps to 2 if there is no rebuffering, and so on and so forth. Right? This kind of a rate model was used. So given this rate model, we were able to show that if you have a pre-buffering SNR of, let's say, 40 dB, during rebuffering, obviously the frame will be constant. Then after post-rebuffering SNR, let's say 30 dB, this kind of a drop is experienced. And we wanted to model this drop because let's say this is your video quality of experience, the blue line, and yellow part is the rebuffering instance, where the video has stalled because there is no video available in the queue to playback. So then it will drop exponentially in that time, and then it can again start playback. So again QoE will start rising. But of course there will be time varying variations in the quality of experience because it's a subjective thing. It also depends, for example, on the content itself, right? You enjoy the content, your quality of experience is better. You are not enjoying the content, the quality of experience will be lower. So it will vary with time, but this drop is coming because of pre-buffering instance, which we want to model as part of our ML model, right? So for all, this evaluation of videos was done by 21 subjects using a slider app. This app was designed in-house by the student, and there was a scoring methodology used, which is single stimulus continuous quality of evaluation, where essentially we followed the IIT recommendations, and the user scrolls a slider in the phone, and this gives a corresponding QoE number between 0 to 100 to the corresponding video, right? So please note there are two possible states here, playback and rebuffering, and an SVR based approach was used in this work where sorry, a support vector regression is used in a playback state with a Gaussian kernel, And an exponentially depreciating QoE model is used in the rebuffering instance. Just give me 1 minute, please. Yes, sorry. Yes. So I was saying we considered two states. One was playback state, and the other one was rebuffering state. And then the user can toggle between any two of these states or the state of the video. So then for this model where we used support vector regression, we applied this kind of QoE expression where we have these exponents applied e to the power minus xm minus xn norm square, and each alpha represents a Lagrange multiplier coefficient, and the xi represent the support vectors over which we are performing this support vector regression, and qf represents the input QoE feature vector, and b is the bias, corresponding bias introduced. There are two types of features we considered. We considered STSQ and the ith order QoE feedback. Right, so these were used to model the QoE, and so this is for a playback state, by the way, right? Now for a rebuffering state, we applied an exponential depreciation e to the power minus gamma over QoE of t minus 1, just like we have done for ETVSQ in the previous study, where QPRB is the pre-rebuffering QoE, QPOB is the post-rebuffering QoE. Then gamma is computed as P1 times QPRB plus PO. Right, P and P1 are linear coefficients which we optimized based on our study. So based on this, ETVSQ was the only work at that point of time which considered rebuffering instances. So we compared our own two works in some sense. So we are able to compare these two, and we are able to show that with NIQE as the VQA metric, it performs best. So please note, a lower OR and a lower RMSE is better because they are in some sense error or outages. Whereas a higher LCC and a higher SROCC is better because they are like positive quantities in some sense, correlation coefficient you can say, right? So higher is better. So that is why NIQE as the VQA metric, SVRQoE, which is the work I just explained, the support vector regression model, performs better in all perspective compared to the existing ETVSQ. So then motivated by this, so this is again the same thing highlighted here, where you have the ground truth collected from the experiment with the various test subjects. The red predicted values are predicted by the SCR model, and the ETVSQ is a dotted line. As you see, there is a substantial gap between ETVSQ compared to the gap between ground truth and the predicted value. And by and large, the predicted values from the SCR model, they are on an average following the trend of the ground truth. This becomes even more evident when we have different type of videos. As you see here, ETVSQ is saturating. If there is some sort of rebuffing and those kind of things, with exponential decay, it may not pick up all the time for all the videos. Whereas the proposed work resulted in better prediction. It was able to follow time varying, time variations in the subjective video quality also. So we also compared this with the existing models. So there are existing models available for just modeling the subjective video quality without the rebuffering instances. So we compared the proposed model, the SCR-QoE model, for example, with the HW model, and as you see here, it performed better on all parameters than the existing state of the art at that point of time. Right. So this is the same thing reflected here. As you see here, the HW model is capturing the time varying, subjectivity of quality of experience, but not as much as the proposed SCR-QoE model. The proposed SCR-QoE model is better. Right. So same thing illustrated here. So then what happened was, by this time, ours was initially the first database, but then by this time several new databases came into literature. So as you see here, this is the timeline of 2017 to 19. Couple of databases came into picture where they also started studying rebuffering instances and those kind of effects and impairments on the video quality and quality of experience. So then just the comparison of the databases available. So this LFO-VIA database is essentially the database generated by Professor Somona, where I was a collaborator, and live and QoE database was in some sense having TVQ, which is time varying quality, but no rebuffering. With videos are available from this database, but metadata was partially available. Now Netflix meanwhile published its own live Netflix database where the time varying quality was available, rebuffering instances was also there, partially some of the videos are available, and metadata was available. For our database, time varying quality was available, rebuffering instances were present, all videos are available because we were the ones who recorded all the videos in some sense, or at least we had the copyright for most of them, all of them, and then metadata was also available. And there was another fourth database, which was live mobile stall 2 database, where time varying quality was not available, but the rebuffering instances were present and full video database was available with metadata, right? It's just to give you a perspective of the state of the art at that point of time in terms of databases. So then, motivated by this, we went on to study the same thing and tried to improve the ML model, and we realized we can use a long-term, short-term memory-based approach for our QoE modeling, or an LSTM model in machine learning. The advantage being that we have a long-term memory of the user in terms of the overall qualitative experience the user has been having while watching this video. And then there are short-term artifacts like short-term variation in the video quality or short-term effects like rebuffering instances, which also affect the video quality. So if we can have a model which captures both of these, in this LSTM case, it captures actually both the long-term and the short-term, variations by using multiple layers. So we have this time distributed dense layer, we have an input layer, and then various LSTM modules in between, where the input outputs are as illustrated. So we optimized it over number of layers and also optimized it over number of units. So we were able to find that a configuration of 2 layers and 22 units works out best. You can increase the layers, but it doesn't significantly improve the performance, right? For the matter of, beyond a certain point, it may reduce also. So with this LSTM based approach, now we had STSQ, which was a short-term subjective quality, and we have a playback indicator, and we have a time elapsed since last rebuffering. These 3 were used as features in some sense. So based on this, we were able to modulate the quality of experience, and the performance results turned out to be really promising. So the LSTM QoE is our proposed work. Meanwhile, there were some other work. For example, NLSS QoE was work proposed by us only in another paper, right? And then there is NARCS QoE. As you see here, for all the measures except OR obviously is minimum for NARCS QoE. For all the other measures, LSTM QoE turned out to be best, right? Same is true for this. As you see here, please note, this is 3, we have considered multiple figures where each one corresponds to the corresponding database. So for example, here, this is essentially what we have done is we are comparing, there are multiple databases available, right? So for all the 4 databases, now we are projecting how these 3 models perform with different VKO metrics. So this is for the first database, the second database, the third database, and the fourth database. So as you see here, for the first database, for most of the features, LSTM works well. For OR, it is not the best, but it is not worse also. It is like 27% compared to 23%, which is the best. For the second database, again, for LCC and FROCC, LSTM works the best, whereas for RMSA and OR, NLSS turns out to be best for this database. For the third database, again, LSTM works well enough, and a closed value for, RMSA and OR. Well, in this case, not very close, but yeah, but still not the worst also. And lastly, for the fourth database, again, it turned out to be the best. So as you see, the performance of the models, but of course, we retrained the model. So for each of the databases, we retrain the model on the corresponding database and then compare the performance. But still, as you see, there is no one unique winner, but on an average, LSTM turns out to be the best, right, in terms of the performance. So then you can also see it here where we have the ground truth and the LSTM based predicted QoE, which is quite closely following the trend. Right. In presence of, so this is a rebuffering instance in some sense, right? That's why the exponential decay. So even in presence of rebuffering instances, it is able to closely follow the ground truth. The predicted value is able to follow, right? So is again the same thing summarized where we have shown for LSTM and the corresponding database with the corresponding QoE model, just to highlight how in most of the scenarios, you know, LSTM performs best, except barring one or two, you know, scenarios. Now, given this, what have we achieved so far? So far we have been able to model the quality of experience using a machine learning model. There are various machine learning models available. You don't necessarily have to use LSTM. You can use NARS also, you can use SPR also, HW also, and LSS also. So given various ML models, we were able to show LSTM works well enough. And then now we want to use this additional knowledge of modeling quality of experience using a ML model to better perform resource allocation, right? So we let us look at this example where you have several Dash servers running, where you have a content delivery network corresponding to each request from various Dash clients. So we have now a base station, which is this eNodeB, where you have multiple UEs or user equipments, each with its own Dash client running in the application, trying to download a video. So this is the setup we are trying to, you know, model. Where what we want is, we want each client to predict the QoE in a continuous fashion using one of the ML models we discussed so far. So it will give its QoE features. There will be a QoE prediction happening through an ML model running at the client side, which will be feeding the QoE back to the Dash client. And then given this QoE prediction, the Dash client with request, you know, corresponding resources should be allocated by the base station. That my current quality of experience is becoming poorer, maybe I need more resources. So this way, now resource allocation for video clients can be done based on the awareness of the quality of experience of the user, right? So let us look at how do we perform resource allocation. So to perform resource allocation, we first need to have a notion of a utility function, because essentially it will become an optimization problem, right? So to solve the optimization problem, let us first agree on what the objective should be. So we can have various kind of objective functions. In this case, the utility function of a user is a function of Q, so that I have an h of Q times 1 minus alpha for 1 minus alpha if alpha is greater than 0, and log of HQ if alpha is equal to 1. So this is also termed as alpha fair utility in the literature, where the idea is by varying values of alpha, you can achieve different degree of fairness. So in this case, HQ is a concave function in Q in the range 0 to infinity, right? Now I can have different, notions of my users. Let's say I can look at cumulative average QoE, which is essentially taking the QoE, Q of tau, averaging it from 1 to t. Let's say 1 upon t outside. I can also look at average throughput, which is essentially 1 upon W throughput computed over a window of W samples. I can also compute per sub-channel throughput, where I take the same thing for a sub-channel only, right? So I divide by this number of sub-channels allocated to this user. Now, for my optimization problem, I can simply optimize an alpha fair utility by allocating, the sub-channels to each user, such that total number of sub-channels is finite. So SIT added over all users is less than equal to S. But of course, SIT for each user I has to be greater than equal to 0. You cannot allocate negative sub-channels, and so that's why SIT belongs to Z plus. And in this case, this is the benchmark system. The H function is nothing but the rate of the user into the number of sub-channels. So this RITH is the rate on sub-channel I, SIT is the corresponding number of sub-channels allocated. So user rate turns out to be, a product of individual rates multiplied with the number of sub-channels. I can try to maximize this and decide the allocation and then compute the quality of experience of the user, or I can replace my objective function with a function HQoE, which is actually a function of QoE of a user I and the number of subchannels. I'm taking a product of QoE and number of subchannels instead of throughput and number of subchannels, and then I can try to optimize my allocation. So we perform this for a realistic LTE kind of a scenario where we have 180 kilohertz subchannels bandwidth, we have 20 dB as penetration loss, 2 gigahertz as carrier frequency. We considered 8 only subchannels for mathematical brevity, but you can always do it for larger number of subchannels also, where this is a traditional base station parameters for a 4G network, right? So for this kind of a setup, we were able to run the simulations and we were able to show that, maybe again I will zoom it a bit. So we were able to show that the network level QoE can be significantly improved for the proposed QoE based resource allocation compared to a throughput based resource allocation scheme. So if you're using a throughput based resource allocation scheme, the QoE is what is there in the blue bar, and as you see, the QoE for the proposed QoE RA is always better, the network level QoE, right? Please also note, as we introduce delay in the system, the performance for the throughput level RA need not, well, it is in some sense degrading, or some sense you can also say improving, but the QoE RA is always performing better, and it is actually independent of the value of alpha. You can vary alpha, and the variation of alpha has an impact on the throughput RA, but it does not have an impact on the QoE RA, which is the proposed scheme, and it is always the maximum possible network level QoE for that corresponding average delay. Another way to look at the results is, as I vary the number of subchannels for a given value of alpha, my network level QoE varies, and in this case the throughput RA increases, the QoE for the throughput RA increases, and it saturates to whatever is the corresponding QoE RA, because as seen here, the QoE RA is always the upper bound. So the throughput RA, as I have more and more number of subchannels available per user, I have more and more resources available per user. That is why the throughput RA is increasing with increasing number of subchannels, and it is saturating to the maximum QoE possible, which is in this case anyway achieved by the QoE RA. Same is true for different values of alpha, where you see the saturation more realistically here and here also, where the idea is, if you have a resource constrained environment where the average number of subchannels available per user is low, then there is significant gap in the proposed QoE performance, which is the red lines, and the existing, let's say, throughput based resource allocation. So in this resource constraint regime, we should definitely be using QoE based resource allocation. If there is not much constraint on resources, we can always use a throughput based RA. The trade-off is the throughput based RA is low complexity, because there is no computation of QoE happening. There is no ML model running at each dash client. Whereas for the UEs with resource constrained environment running QoE RA, each UE has to run that ML model, right? So that's the additional complexity, because of which this gain is observed, in this regime. So same thing is tabulated here in terms of the percentage reduction in the average rebuffering time now, using the proposed method with SVR QoE as the ML model for throughput RA, and as you see, there is substantial reduction in the average rebuffering time, right? Same thing now redone for LSTM model. So the earlier one was SCR model, right? Now same thing done for LSTM model, and there also you can see that substantial gains can be obtained, right? So maybe here I would like to conclude the talk, and I would be very happy to answer any questions or any comments or any queries. Yes.
Sir, thank you very much, sir. Really, it's an interesting session. Participants, if we want to ask any question, please.
I have also projected my email ID. If just in case later also you think you have something you want to clarify,
Yeah.
feel free to share. Just connect with me on email, and I'll be very happy to answer any queries that there.
Sir, then I think there are no questions from the participants. So thank you, sir. On behalf of this AICT ATAL FDP, I thank you for your presentation. It's for really a nice, informative presentation. Thank you, sir.
Thank you. Thanks a lot. And I am again, my apologies for the
No, no,
inconvenience caused
no, no, sir, no,
due to
sir.
the delay. Yes,
We are waiting actually, but I little bit tension, and at that time we are not lifting the call. That's it, sir. Otherwise, everything is okay.
yes, sure, sure. Thank you. Thank you for inviting me. And
Yeah.
please feel free to drop